Greetings and welcome to experiment number 3 of Mechanical System Analysis Laboratory. The name of this experiment is CFD Analysis of Flow over a Circular Cylinder. So in this particular assess, these are the contents of this experiment. Initially, we'll see what are the practical cases for external flow, that is flow over a non-flat surface or circular cylinder or sphere. Then we'll study how the pressure and velocity varies when flow over takes place over cylinder or airfoil section. In this case, we will see the flow physics over a cylinder. Then we see how to write or how to develop a program for flow analysis over a cylinder. Finally, we'll develop the pressure and velocity variation. Then the position of stagnation point for rotating as well as stationary cylinder, and with conclusions. So these are the points. But again, the main objective of this experiment is to interact with coding part. That is the main objective, understanding of the coding part, because the theoretical part you already learned in fluid mechanics in second year of engineering. So if you see the application of flow over cylinder or sphere, so these are some of applications. So application when the flow takes place over a smooth sphere, maybe a ball or a golf ball. So you can see the variation between the flow pattern. So generally the main objective of this flow analysis is to understand the flow pattern across these objects, cylinder or sphere. And you can see what is the effect of the roughness on the flow pattern. So you can easily visualize. So main objective is to recognize various important points, that is a separation point where the flow separates. You can see where the flow separates, what are the stagnation areas, and these are the wake areas. So these are the three important parameters are studied during the flow analysis over a cylinder and a sphere. So these are the applications. So generally when the flow takes place over a cylinder or sphere, so such kind of flow patterns are developed, and CFD plays a very important role while understanding the flow physics, especially when the cylinders are arranged in line, cylinders are arranged in stagger arrangements. So mainly cooling coils. Suppose this is the example of shell and tube heat exchanger where the flow takes place across tube bundles. So this is a case of flow over a cylinder. Similarly, when the flow takes place over in cooling tower, again the flow over the coil surface or bundle of coils. That is again example of flow over cylinder. And in those cases, sometimes the cylinders or the pipes are arranged in line, or sometimes they are arranged in stagger arrangement. So with the help of this flow analysis, we can understand where the pressure losses are more, where the wake region, where the losses occurred more. So accordingly, we can rectify or modify our design. So these are some practical examples, actually, where the flow takes place over a cylinder or sphere. So such kind of flow physics can easily be analyzed before manufacturing of these devices, and accordingly the modifications are made. Now the flow takes place over a non-flat surface, especially over a sphere or cylinder. There are three types of forces acting: inertia forces, viscous force, and a pressure force. So generally inertia force and viscous force are present even during the flow takes place over a flat surface. But the pressure force is mainly added here. And there are two possible cases. In few cases, the pressure force assists the inertia force. In that case, the pressure gradient is negative, means pressure decreases along the direction of flow. And this is a favorable situation because in that case, there are less losses and high efficiencies because the flow is accelerating. So this is the case which need to be maintained because in this particular case, the flow accelerates and the losses are less. In another case, where the pressure force assists the viscous force, means the pressure force acts opposite to the direction of motion. So in that case, the pressure gradient is greater than zero. So this is an unfavorable situation where there is a possibility of separation, possibility of wake regions. And due to this, there are heavy losses occurred because of the turbulence at the downstream region. So that's why case one is mainly a favorable situation. But in some cases, in flow or cylinder or sphere, it is unavoidable. Only we can extend the stagnation area, or we can extend, we can prolong the separation zone so that to minimize the wake region. And accordingly, we can minimize the drag force. So you can see the example how the flow is taking place when the how the flow pattern is taking place. On the right hand side, the flow is turbulence. So you can visualize where the flow separates here itself, which is not a desirable. And because of this, the heavy wake region is created here. But if the flow is laminar, the wake region is very low, so losses are less. So this particular cylinder experience less drag force compared to this. So there are majorly in flow cylinder or sphere. So in this case, the pressure losses are more. In this case, the pressure losses are less. So this kind of flow pattern can easily visualize using a CFD analysis. And this is an attempt because CFD analysis, you can visualize the picture, but what is happening at the back end? So how to write the program for such kind of situation? That part, that basic part, we are going to learn here. So this is, you can see the flow over, that is when turbulent flow taking place, when laminar flow taking place. In both cases, you can visualize the flow pattern. So same kind of visualization you can do even during these things, that is CFD analysis. So boundary layer separation or non-flat surface. So this is a section of the, we can say, cylinder or sphere, and this is a flow passage. So during this flow passage from A to C, the flow is accelerating. So pressure gradient is negative, we can see. And from B to E, you can see the pressure gradient is positive. And there is a possibility of separation at this particular point. And there is a possibility of reversal flow so that the velocity is negative in this particular zone. And the heavy losses occurred because this the boundary layer thickness also increases drastically, and due to that, this particular portion experiences a more drag force, that is the force against the direction of motion. So because pressure force assists to viscous force in this particular zone, and the pressure force assists the inertia force in this particular zone. So if you see the pressure variation in this particular cross section, that is first convergence section and then divergence section, the pressure decreases, then it reaches to the lowest level, and then pressure increases. So this is the pressure variation. Similarly, velocity variation is opposite to that, where the pressure is lowest, the velocity is highest, according to the Bernoulli's theorem. So this flow patterns, or this variation of velocity and pressure, we can analyze using a code. Obviously, we are using a Silab coding here. So this is the situation where the boundary layer separation takes place when the flow takes place at over a sphere or cylinder portion. So there are different conditions. So in this particular favorable zone, that is from A to C, A to B, we can say, the pressure gradient is negative and the velocity gradient is positive. So flow is attached. From C, the pressure up to, from B to C, the pressure gradient is positive, but still the flow is attached. So this is not we can adverse pressure gradient, we can say. But beyond point C, there is a possibility of adverse pressure gradient because of separation of flow takes place from C to E, and where the velocity gradient is negative. Velocity gradient is zero at point C. So these are the various characteristics when the flow takes place over a sphere or cylinder. And the lots of ADs are formed that we already seen in that particular video, short clip. So the ADs are formed at the downstream, and which disturb the flow, and there is a disturbed region in which eddies are formed. That particular region is called as a turbulent wake. So we have visualized that particular flow. So such kind of visualization we can investigate when the flow takes through a CFD analysis. But in this particular case, we'll just make an attempt to understand the variation of velocity and pressure when the flow takes place over a cylinder or sphere. Now, in order to calculate the pressure at a one particular point, we can use the Bernoulli's equation. And Bernoulli's equation, that is just before the entry, that is few meter before the domain of the cylinder. So where the pressure is atmospheric and the velocity is mainstream velocity. And the pressure at any point on the cylinder. So that varies with angle as well. So this is according to the Bernoulli's equation, considering the no loss, we can say the pressure energy plus kinetic energy. So total energy remains constant. So this total energy remains constant. That means that is only possible in ideal case, not in viscous, not in real fluid. But we'll study the ideal case. So where the parameter, you can see that PO is the pressure in the uniform flow at some distance ahead of the cylinder, that we just before the entry of the flow domain of the cylinder. U is again the mainstream velocity, or we can say free velocity, that is uniform velocity. So before it comes in contact with the cylinder, obviously. P is the pressure at any point on the cylinder, and U is the velocity at any point on the surface of the cylinder. So that is U. So according to the formula, that U is nothing but 2U sine theta plus circulation divided by 2 pi r. This is the formula for U. I will not go in depth of the derivation of the U. That is the U, that is the velocity of flow, which is a function of the mainstream velocity as well as the circulation, that is circulation, and 2 pi r. So accordingly, if we substitute instead of small u in this value, and if we resolve, we can develop equation of pressure at any point on a cylinder. And this particular equation we use in Silab to get the pressure variation with respect to theta. So in Silab, we are again, like previous experiment, again, we take one example, and the same example we solve using a Silab program. So in this case, we have considered the cylinder diameter is 1.8 meter and its length is 1.2 meter. And it rotates at 240 RPM. So the cylinder rotates in this case with its axis perpendicular to the stream of water flowing at a velocity of 15 meter per second. So in this case, we are, instead of water, we consider air also. So it doesn't happen. Assuming no slip between cylinder and circulating flow, and determine what is the pressure and velocity variation across the cylinder, and the position of stagnation points, where the stagnation points occurs for rotating and a stationary cylinder. Now, there are some limitations in Silab programming because that we cannot get the contour of the velocity and pressure, but we get the variation of velocity and pressure with the help of these examples. Now, Silab programming is generally done that Silab 6.1.1 you are using. And this particular code you can write in Silab notes, which you already studied in prerequisites video, where to write the program, how to execute the program. So that part I'm not covering in this particular experiment. So first of all, we'll write the given quantities like how we solve the problem numerically. In the same way we write the programs. It's a simple steps. So diameter is given, then length of the cylinder is given, then RPM of the rotating cylinder is given, velocity of water in meter per second is given. Density of water is 1.2 we have considered. In fact, it's a typo error. This velocity of air we are considering as a fluid. So that's rho is 1.2, it's density of air. And then pressure we can consider with respect to atmosphere, that is pressure is 0 we are considering. And theta value, that is variation of theta, that is 0 to 180 degree with the interval of 10 degree. Then this is velocity, that is the linear velocity of the cylinder, that is pi dn by 60. then the tau we are using, then u, that u velocity we can uh, that is considered, that how to calculate u. So these are the expressions we already studied in previous slides. So the same expressions we can write. Now we have to get the variation of pressure across the cylinder. So this is the equation. We write the expression in Silab coding. So nothing difficult, only instead of multiplication sign, we use star sign. And the same notations, whatever the notations we have used to define the parameter earlier we have defined. So we write the expression of P. Any equation we can write, then we use the plot function. So that is theta versus P with some marker is used, again star marker. Then we label that x-axis we have angle in degree, on y-axis we have pressure in Pascal. And we write the title, that is a pressure variation for a cylinder you can write. So that's it, this is the program. If you execute this particular program, you'll get the pressure variation across the cylinder. So at the entry, that angle is 0. So its angle is up to 180. So there is a continuous decrease of pressure that we already seen in that one theory part, that is how the boundary layer develops over the cylinder. So pressure decreases where during the conversion portion, it achieve the lowest value here at 90 degree. And then the pressure increases. So it's a uniform pattern because there is no viscosity place. So viscosity part is not considered here. So that's why it is there is a uniform pressure distribution. So there is no drag force, we can say, because the pressure variation is. So this is the pressure variation with respect to angle when the flow takes place from one end of the cylinder to another end of the cylinder. So pressure gets lowest at the 90 degree, that is at the center of the cylinder. Similarly, we can write Silab programming for velocity variation. So for velocity variation, most of the parameter remains same. Only in this case, we consider the velocity. So we'll not take the pressure part. So because we want to see the variation of velocity, so only velocity, and take a plot of velocity. So that is velocity, that is a velocity at any point versus this thing theta. So you can already you can write theta comma u, or if this program I have part of the program I have removed. So that's why I have in the already we have initially in the plot we have considered that theta. So the same things, then labeling, that is X label, Y label, and the titles. And once you execute the program in Silab node, you'll get this profile. Now exactly the reverse profile we can see that velocity increases as in the accelerating portion. It reaches the maximum pressure velocity at the center, that is at 90 degree, where the pressure is lowest, and again the velocity decreases in the downstream zone. So this is the velocity variation when the flow takes place over a cylinder. And again, as the uniform structure you are observing from both sides from the center, that is because of not considering the losses, because we have considered only Bernoulli's equation. Further steps, next level, we can consider the losses, and we will see on the right-hand side the variations, means non-symmetric variation you can visualize. Then the location of a stagnation point, where the stagnation point is the point at which velocity is 0. So in order to understand the stagnation point, same velocity, because this is a rotating cylinder, we consider the theta value that is from 0 to 360 degree. So we'll see the stagnation point where it arises. And we can see all the remaining steps are same. And we take same plot, that is u versus angle, labeling the part. And if we see the position, now you can see the stagnation for rotating cylinder. The stagnation point arises at two locations, one at 230 degree and other at 310 degrees. So when the cylinder is rotating, then the stagnation points arises at the bottom portion of the cylinder, not at the upper portion of the cylinder. So you can see here the stagnation portion is around. So this is a favorable situation, because in that case the wake region is not at the downstream side, that is at the bottom side. So this is good for lift force. So especially rotating cylinder, it helps to lift that particular, or because the lifting force is high. But generally for most of the practical cases, we come across what are the applications where there is only the question of stagnation or stationary cylinders. So stationary cylinders, because most of the pipes, most of the heat exchangers where the pipes are stationary, not rotating. So under that circumstances, if we for stationary cylinder, only if we put n is equal to 0, you're getting stagnation points at 0 degree and 180 degree. So that is at the that extreme upstream side and downstream side. That is symmetric. But again, this is ideal case. In case of considering the this viscous forces, or we can say boundary layer theory for real fluid, it is somewhere at that is in between 100 degree, or we can say below 180 degree, not exactly at the 180 degree. This is only possible when the ideal fluid flows over the cylinder. In that case, uh, the exact stagnation point or separation point occurs here. So this is again, so such kind of variation we can easily analyze using Silab program. So this is simple Silab program, but even it's simple, but we get the variation at each and every point on the cylinder. So for getting this variation during analytical approach or solving numerical, you need to solve, suppose if we have considered these points, so many times we need to do the calculations. So in Silab programming, you'll within a fraction of second, you get the value of velocity or pressure at any point on the cylinder. So this is a cylinder. This is the upper portion of the cylinder. This is the lower portion of the cylinder. So at any portion point, you can see the velocity. What is the velocity at that point? So that is the beauty of writing the code or writing the program. And the same code is generally written at the back end of the CFD, that is computational fluid dynamics, and only we can see at the upper, we can see it on the screen, that is the colorful images. But on the back end, you're supposed to perform this kind of coding. And for developing such codes, the fundamental, the one must be fundamentally strong. So that's it about this experiment. After the end of this particular experiment, you could able to explain the concept of boundary layer separation, what are the important parameters in the boundary layer separations. So you could able to discuss how the flow or sphere or cylinder taking place, what is the variation of velocity and pressure, what are the important characteristics when the flow takes place, and what are the conditions when the flow is attached, when the flow is detach, when it's at the point of separation, and how to modify your design after analysis, that you could able to discuss when the flow takes place over a cylinder or sphere. Then you could able to write a small program for getting pressure and velocity variations. You could able to develop pressure and velocity variation plots also. Then you could able to identify the position of stagnation points for rotating and stationary cylinder. Even for rotating cylinder up, you can check how the velocity, if we change the velocity speed, how it affects on the stagnation and equation. So that you can easily investigate using programming, which takes more time in actual performing the calculations. So that's it from this particular experiment. Thank you very much.